All right, hello everyone. Oh, here comes the official countdown from Jess. Uh, Thank you for all attending week 4 of Fundamentals of Gaseous Halos. And I think we are down with this routine, but there might be some new people this week as our topic shifts to our own halo. So I have our standard introductory slide here where we talk about Zoom and how we run this program. And we encourage people to mute yourself when not speaking, of course, and I think people are very good at that. And reactions are great in Zoom, such as raising your hand. You can always change your display name. And I haven't yet because I'm still named Cameron Hummels. But you can do this every time and add your pronouns as well. And a lot of people use chat window in Zoom, and that's okay. But it's also important to also use the associated KITP Slack channel. And this week, the Slack channel is Halo 21 Week 4 Our Galaxy, and for questions and comments related to the presentations. Of course, these are being recorded, the presentations, especially on Tuesday and Thursday, and the tutorials on Wednesday. Mondays and Fridays, especially the speed collaboration and the collaborative discussions, are not recorded. Those are more open-ended, where you can feel free to say what's really on your mind. All right, here we go. So this week is the Milky Way Halo Week. What does the Milky Way tell us about gaseous halos? And I'm very excited about this week because our halo is very complex, and we're learning a lot of new things about it from recent observations. So while last week was pretty intense, I thought it was very theoretically oriented, a lot of really nice idealized simulations, beautiful simulations. This week, I think we'll have a combination of a lot of observations spanning many multi-wavelengths, from the hot to the cool to everything in between. I think we've had some really recent amazing results about the Milky Way. We will learn this week, both from the gaseous perspective, but also, something that I have been kind of following with a lot of interest is some of these Gaia results and the chemical tagging of stars in our halo, as well, telling us about the history of the Milky Way in a new way, and how our merger history might likely determines the status of our galaxy, of our halo. So I'm looking forward to having a interdisciplinary discussion of that, of all the methods that we're focusing on in this program. Of course, we encourage you to take the survey. Still, the week 3 survey is up, and if you fill that out by the end, midday today, the organizers, we will synthesize these results. Already we got about 30 responses, and every week's survey is different. They're targeted. They really take only a couple minutes, and if you want to fill out more, we encourage you to do that, but you can get through it in 1 or 2 minutes. And the link for it is in Halo 21 General Slack. And already we've integrated a little bit of that advice into this week from last week's survey that was put out on Friday. Okay, so we had something new last week. We had, I forgot to ask, I hope everyone had a relaxing weekend. I kind of didn't. It was kind of an intense weekend. But we had a really fun time on Friday night. We have this entertainment budget from thanks to KITP, and we used it to a great effect on Friday night with Jet City Trivia, and that was fun. It was about 90 minutes, and there were about 22 of us, and significant others and children were invited. They all helped We had 7 teams of 3, actually 6 teams of 3 and 1 team of 4, and that 1 team of 4 won the quiz contest in dramatic fashion in a tiebreaker, which came down to the end. I was on the other team, and so congratulations to Cameron, Fari, Johnny, and Zach for getting figuring out how many miles was in the original Route 66. I think maybe we'll do this again, Jess, and maybe we'll have a more international theme. I don't know. It'd be fun, and we'll do some other things. Maybe not this week, but I think we should try to aim for another social hour next week, perhaps. Okay, we have this Halo 21 new results YouTube channel is really building up a lot of great results, and already. You can see that I just took a snapshot of this, and there's already, if I count up, at least like about 25 videos up there, and there's about 8 new results video from week 3 and week 4, and these are all 4-minute videos, and they're very, very well done. And I want to highlight this week's videos. I think I got, well, actually it's week 3 and some week 4 ones, and they don't necessarily have to be exactly on that week's topic, but often they are. So I want to give a shout out to Mandy Chen, Aaron Betcher, Ed Bowie II, Devrat Prasad, Phil Carrot, Hannah Bish, Rajeshwari Dutta, and Priyanka Singh. And I've watched 7 out of the 8. Priyanka just put hers up last night, so I definitely recommend all of them. And I think this will be great because it is a way for everyone to be involved, and you can put up more than one. Just a reminder that it should be either something that's not published or published within the last calendar year. And we also have on the Fundamentals of Gaseous Halos YouTube channel a separate playlist for researchers on the job market, and it's also cross-posted in the Slack channel Halo 21 on the market. It's up to a 15-minute presentations, and there's one, a shout out to Paco Holgren for being the first, and I watched that. I learned a lot about his cosmic ray simulations, wind tube simulations, and some interesting, some additional work on UV radiation from stars, some theoretical calculations on that. So highly recommended, and I think that will continue to be populated. There's no rush on that. It will be always there and preserved on YouTube. Okay, so let's get to this week's exciting program, and we have 2 featured conversations, and the first one is Halo 21 Milky Way, Our Own Atmosphere by Jessica Werk, there she is, and Yong Zheng, and they are very well organized. Probably more so than the conversation group I ran a couple weeks ago. So everything is improving, and I also it looks like Shmuel Bialy and Miao Li have collaborated on a nice presentation on the analogies and differences between the ISM and CGM, the Halo 21 ISM-CGM channel. So they will begin the featured conversation today in the first part of the program today, and have a short presentation up to 15 minutes each. And then, of course, we will have speed collaboration. And I'm going to give a note about that based on some feedback we got. So they will have actually an after party, as they will talk about at some point, or at least one of them will. And so we'll hear about that in a little bit. So Tuesday we have a featured talk by Mary Putman. I'm very excited about that. Mary is the only person I see in person who attends this meeting. More about that later. And she has a great panel that she helped select. Gertina Besla, Edmund Hodges-Klook, Chris Hauk, and Freke van der Voort. So that will be very nice tomorrow. I'm sure that will get a big audience. Then we have Wednesday tutorials, and we do have 3 again, and we won't ever have more than 3. And that can be a pretty intense day. A lot going on, a lot of breakout sessions afterwards, a lot of discussion in the Slack channels. So this week we have Kartik Sarkar talking about the family bubbles. Then Marcus Bergen talking about the related but newly discovered E Rosita bubbles. And then, and I like this, Yang Zheng will have like a true tutorial, how to deblend the Milky Way ISM from the CGM. And that is such a difficult topic. It does definitely deserve its own tutorial. So I will attend all 3. And then Thursday, we have Filippo Fraternelli talking in a more theoretical keynote presentation. And we had a lot of people for this panel. It was hard to decide, so we made it a larger panel. Jakob Fairman, Miao Li, Nir Mandekar, Frank Vandenbosch, and Jess again. And of course, Filippo and the keynote speakers on the panel as well. And that goes from, the panel goes from the second hour from 9 to 10 a.m. Okay, I'm going to take a drink of water here. And I'm about to turn this over to our first ongoing or featured conversation, but a couple Slack tips, because I think people are pretty well practiced at this, but we definitely encourage you to put a picture up of yourself on the Slack channel, and it's not too hard to do, along with other things, everything about your name, you can pronunciation, that's helpful, affiliation, pronouns, etc. And it's easy to change your preferences as well. Feel free to ask one of us. I haven't used Slack the way I have until this program, and I keep on learning things, and I'm one of the organizers, so it's never too late to learn. Of course, we have this Slack channels listed, and you have the channel browser, and it's a long list, but it's well organized, and you can go in between channels and follow the ones you are interested in. And there's our channel, week 4, Our Galaxy, for this week's program. Pins are useful. Last week, from the collaborative discussion, we had Cameron post summaries of the 2 questions, the 2 Menti voted questions that we decided, and he pinned the results up on there. So you can feel free to pin things that are important in the separate Slack sub-channels as well. Let's see, is that it? Oh, other advice. Feel free to, as we have panel discussions, such as on Tuesday and Thursday, to use Slack to ask questions to the panel after the keynote speech, and it's okay to give thumbs up or even thumbs down, and then that way the panel knows, or other reactions to it, and that way the panel knows what is the audience interested in, what are the participants, what do they want to hear about next. So I am going to stop the share. I've gone on long enough. And I am going to turn it over to Jess and Yang, I believe, who are going to talk about our first featured conversation.
Okay, so thanks, Yang. So we're going to start out with a little experiment, but first I guess I'll give you some context. So because the Milky Way is our own galaxy, we have treasure troves of data that uniquely constrain its properties. But also, as we'll hear from Yong, because it's our own galaxy, it makes it much more complicated to study. My PhD thesis advisor, Mary Putman, used to say, we're like a meatball in a plate of spaghetti. And I really love that analogy. It makes me happy. Okay, so, but the thread that kind of unites a lot of the topics we wish to discuss in our channel, Halo 21 Milky Way, ultimately kind of comes back to this age-old question: is the Milky Way actually an L-star galaxy? Not only in terms of its stellar content, the content of its gaseous disk, but also in terms of its gaseous atmosphere. I think ultimately we're seeking to understand the Milky Way in the broader context of the universe. So this question kind of drives to the heart of the matter and links a lot of the individual questions that Yong will introduce in a minute. So just quickly, the answer to this question is almost certainly yes in some ways, no in others. It depends on what you mean. There's lots of gray area, lots of nuance. That's what we will discuss this week. We'll live in the gray area. We love nuance, right? But for right now, I want you to go to menti.com. Those of you who've been to the Friday discussions know exactly how to do this, okay? Just go to menti.com, easy, MENTI.com. Enter code 162507. The zero is important there. 2, okay? That gets you to the vote. And I want to know where you all stand right now at this moment before we begin our nuanced discussion. And if you think it's more yes an L-star galaxy, then no, vote yes. If you think it's more not an L-star galaxy, vote no. And if you really have zero opinion whatsoever, which is hard for me to imagine, just abstain and let me know that you're present, you're alive, you're here thinking, and I am just gonna, sit here for 30 seconds while you all think about it and vote, and I'm gonna tell you the answer right now in real time. This is the amazing thing about Menti. I'm watching the votes come in. 27 people have voted. This is really interesting right now because I totally disagree with this vote. So hopefully, this week maybe will change your minds. So, oh, Ben, thanks for that. An L-star galaxy and a typical L-star galaxy are different in my book. That's really interesting. All right, maybe we'll talk about that later too.
My answers would be different to those two questions, but
there is a lot of gray area, Mark. It's absolutely true. So I've seen 52, 53 votes. Votes are still coming in. So just hang tight for a second, but I see the way this is going clearly. 56. All right, 20 seconds to vote. It's not hard. Menti.com, enter that code. You can do it on your phone even. Menti.com is super easy for real-time polls. We're using it in the Friday discussions. This is a little different. I'm watching your votes come in. 10, 9, 8. Really? There's 96 of you here and only 61 of you have voted. Come on. How much is Menti paying you? You know what? Good point, Drummond. $0 right now, but you never know. All right, well, 61 of you voted. Oh, 62. Some of you are truly abstaining, which I find very interesting. This is totally anonymous. Nobody's going to make fun of you. For your answer. Nobody's going to know. I just want to get a baseline of where we are. Where are we starting from with this group? All right, I'm going to stop the voting. All right, so are you ready? Drum roll. With 65 votes in, we have 37 for yes, the Milky Way is mostly a typical Z of 0 L-star galaxy. 37 out of 65. That's more than half of you. Only 18 say no, or mostly probably not, right? 18 say no, and 10 of you decided to totally abstain. You have a fully open mind. You're ready to learn this week. All right, well, that was a really interesting experiment. Let's carry on. So we realize our channel name is a little broad, right? And there are a lot of other channels that are going to overlap with some of the topics that we'll cover. And this is a non-comprehensive list of some of the other Halo 21 channels that are certainly relevant to this week's discussion. We're not, trying to be exclusive. We'll try to not focus on some of the other things this channel will focus on, like the disk halo interface or X-ray observations of the Milky Way halo. But what we really want to do with our channel is unite a number of observers that use totally different methods, from pulsar dispersion measure to X-ray emission to UV absorption, and studying the Milky Way halo specifically. I just love this idea of uniting our communities in service of truly trying to make progress on understanding the Milky Way. And with that said, this is just the start of the conversation. We're just telling you, that this is happening. Go to that channel, Halo 21 Milky Way. I've already posed some questions there, trying to get the conversation started, but we're having an after party. That's what these separate Zooms are called. So the link is actually posted in Halo 21 Milky Way. I'll go ahead and pin it to the channel, but hopefully you can make it. Yong and I decided on Wednesday, February 3rd, 12 p.m. to 1 p.m. Pacific time. And so that's after the tutorials, gives you a 2-hour break after the tutorials. Come to the after party. It'll be awesome. I'm hoping to get as many people as possible there, just to really kind of settle on what we want to focus on this week for our topics. And so the next view that you can see here is this beautiful, and maybe we'll see this again this week many times, is this groundbreaking 3D rendering of the Milky Way's gaseous structure from the Putnam, Peak, and Young review in 2012. And you can see, historically, we've known a lot about the H121 centimeter emission from the Milky Way halo, and recently we've been able to place distance constraints on a lot of these structures, from high velocity clouds to intermediate velocity clouds, that are all kind of within 10 kiloparsecs of the Milky Way plane. Of course, there's so much more. There's different phases of material. I think Yong has drawn the Fermi bubbles there on top of Mary's beautiful PDF figure. And then if you zoom out, right, you see that I think one of the things that makes the Milky Way really unique among L-star galaxies is this honking Magellanic stream that it has, featuring the LMC and the SMC. And I'll tell you, I lost a bet like 5 years ago. I'm still bitter about it. Actually, it might have been like 6 years ago with X Prochaska about, is the LMC a dwarf galaxy? I think a lot of people think of it as like a low mass galaxy. It's got more, and I lost a bet. I thought it was. It's not. It's got more than 10 to the 9 solar masses of stars in it alone. Like, the LMC is not a dwarf galaxy. It's interacting with the SMC. We'll hear more about it. That's still a dwarf. Gertina says that that's still a dwarf. Not in my mind. I feel like you have to be less than 10 to the 8 solar masses to be a dwarf. Maybe that can be another thing we vote on later this week. Okay, so finally, just to kind of drive home the idea behind this channel, it's just that, we're now holding in our hands all sky maps in H121 centimeter emission, deeper than ever before, 3D dust polarization maps, H-alpha emission maps from WAM, and more, catalogs of stellar masses, distances and ages based on Gaia, large spectroscopic surveys of the Milky Way in combination with high quality data. And you can see here I've overplotted the hundreds of high quality UV sightlines that really just present this singular opportunity to study the spatial distribution, kinematics of the CGM of the Milky Way in unprecedented detail. From an observational standpoint, I think we are in the age of the Milky Way. The next like 5 to 10 years, I think Milky Way all the way. Okay, and then finally, not only observations, but I think some of the most beautiful high resolution idealized simulations are starting to come out. The one that I'm featuring here is one that is I just find stunning is the Tigris model from Chang-Gu Kim and Eva Ostreicher. They have a series of papers highlighting this model. One of my favorite things about it is it actually just very naturally generates this galactic fountain that alternates in periods of about 50 to 100 million years of outflow dominated periods and inflow dominated periods. They can predict line of sight velocities. And so it's just, to me, it's inspirational. So yeah, and that's all I have to say. Now Yong's going to talk about some of the specific questions that we want to talk about in our conversation group.
Yeah, thank you, Jess. So Jess and I worked together and identified 7 topics we would like everyone to talk about. And of course, this is by no means covering all the things that are interested to all of you. So if there are any things that has not been mentioned here but I would like to talk about, feel free to bring it up during the discussions or go ahead, post the questions and comments on Slack. The first topic we identify is about the gas kinematics in the Milky Way. And I think Filippo might talk about it on Thursday's keynote talk as well. Specifically, as we highlight in a cartoon illustration here, we are thinking about the disk rotation, the halo lagging, and the disk halo interface. And then the halo rotation. There are several questions we would like to ask. For example, are the Milky Way's gaseous structure co-rotating with the galaxy? And there have been many different kinds of work from H1, UV, and X-ray emitting gas as shown in the right panel here. And if yes, does the gas rotate in different rates from phase to phase? Because the last question we wanted to ask is because we sit inside the Milky Way, does the halo rotation affect our understanding of the line of sight gas kinematics? The second topic we would like to highlight is about the high velocity clouds, and I believe Mary will talk about this thoroughly tomorrow. And specifically, we are interested in what's the gas inflow rate and outflow rate for the HVC, and are there any connections between HVCs and intermediate velocity clouds, low velocity clouds, and the general extended Milky Way CGM. The third question has come up a lot in previous discussions. For example, how do the ionized and neutral gas phases related to each other? As we heard from Drummond and many others have discussed this on the Slacks, perhaps the answer lies in the turbulent mixing layer. So we look forward to hear more discussions on this. The third topics, which will be covered on Wednesday's tutorial by Marcus Bruggens and Kartik Sakra, which is about the Fermi bubbles and the Eurosita bubbles. And so we are not trying to bring out a lot of questions here, but I saw this discussion on one of the Slack, which is it's a North Polar Spur, which is this feature here, I believe. It's a North Polar Spur, a foreground feature much closer to us than the Fermi bubbles. Are there a clear distance estimate for it right now? And the other question we would like to ask is, are the Fermi bubbles, which is on the left here, and the Eurosita bubbles, which is on the right here, the same features? And then eventually, are these bubbles AGN-driven or super feedback-driven? And can we see different signatures in it? The fourth question is also related to cloud structures, and this is something we saw a lot of discussion so far as well. And it's about clouds in different sizes, from cloudless to complex to streams. On the left here, we are showing you 2 figures from H1 21 centimeter observations that shows you the clump size distribution and emissions. And on the right here, we are showing you the UV absorption line data in different kinds of ion that shows you 2-point correlation functions of different ions and showing you how they correlated spatially. So the questions we would like to ask is, how does the clump size distribution from the UV data and the H1 data relate to each other? Because I feel like right now, when we have all this discussion about clump size distributions, it's not clear which kind of data we are talking about, what kind of connections we are talking about. The other thing we would like to discuss is the northern and southern asymmetry. This is something we have seen in both H1 and UV and X-ray, even though we didn't put the plots here. The fifth question is about the magnetic fields. And so we have talked about magnetic fields in different occasions, for example, in the fast radio burst tutorial led by X. And I would like to highlight this work, which shows you the magnetic field measurement towards the smooth cloud, which shows that the magnetic field in that high velocity clouds have a strength about 5 microgauss, which is pretty strong, and that is comparable to the ISM measurement we have so far. Related, last week we talked about the non-thermal process, so we would like to ask, how can we explain the observed properties of high-velocity clouds with the presence of magnetic fields and cosmic rays? Specifically, we would like to ask, how about the velocity, mass, morphology, and cloud size distribution? How do they change from one model to the other model, and which model best represent the observed data? The fifth topic, Ben has quickly alluded to, which is about the observational biases, or how to deploy the ISM and the CGM. And this is mostly because we sit inside the Milky Way and we observe everything from the inside out angle. So I'll let a tutorial on Wednesday to talk about these topics. Finally, we would like to jump out of the Milky Way and think about the bigger environment, which is the M31 CGM and the local groove medians. And some questions here, for example, what's the difference between M31 or Milky Way, or are they similar to each other? And then, is there the local groove median? And there's a recent paper by Mary that talks about this using observational data. So I look forward to tomorrow's talk very much. And then finally, there's a recent paper led by Zhijie Qu, which talks about maybe there is a hot gas bridge between the Milky Way and M31. If so, can we identify that gas bridge in data, and can we see this in cosmological simulation as illustrated here by NUSA 2014. All right, so that's all the topics we have thought about, but if there's anything that has not been covered here, feel free to ask or post the questions on Slack. Thank you. Ben.
Okay, thank you, Yang. That was excellent. Wow, that was a really nice summary, and thank you, Jess, for that. And that was a nice presentation. That was about 10 minutes. Excellent start to the week. I'm looking forward to that after party as well. Okay, so we have another featured conversation between Shmuel and Miao, and I will let one of them share their screens if they can. There we go. Okay, and I will mute myself and let Shmuel start talking.
I think Miao wanted to start first, and then I'll go.
Sounds good. Yes.
So can you all see my screen?
Yep.
Okay, I cannot hear you, but yeah, I assume you can do that. Otherwise, someone will probably shout out something. Anyway, so yes, so we have this Halo 21 ISM-CGM conversation group, and actually there are many interesting related topics. So and also I think is very closely connected of weeks. So, you know, we would like you to share your thoughts, share your questions on this channel, and maybe we'll schedule an after party at some point.
Miao, it seems you have a connection problem.
I'm eager.
Yes, it's a big problem. You're right. Thank you.
Yeah, Miao, we're having a lot of trouble hearing you just because your audio is really breaking up. I don't know if there's another like microphone you can use or.
What I can do, maybe I'll start. Meanwhile, Mia, you will try to fix that. So I'll jump to. Okay, so.
Sounds good. Yeah.
Okay, so I'll jump. Okay, so I hope you can hear me and also see me. See the presentation. Yes. Okay. So basically, what we thought could be nice for this channel, we separated the discussion of the ISM-CGM into two parts. One is connection between the physical connection, so the interface of the ISM and CGM and the flows of gas between the ISM and CGM, and that's what Miao wanted to talk about, and she'll talk in a minute. And The other, I think, interesting aspect which I wanted to bring up, and please join us in this conversation in the Slack channel, is physical processes that are similar and different. So hearing the discussions throughout the weeks, I hear so much familiar stuff that we talk about in the ISM community, and now you talk in the CGM community, but the scales are different and the temperatures are different, but it's often similar processes. And the reason why I think making these analogies might be very useful is not just because, it's like a new agey thing, everything is the same, and that's not the thing. It's really, I think that if you have over large scales of, physical scales, energy scales, temperature scales, things that are similar, say the multi-phase nature of the gas or the role of turbulence, things like this. And if we're able to make this full analogy list and identify what is the physical process that makes the gas multi-phase, or what's the role of turbulence, and now this applies on very large scales of energy and density and temperature, then we might be getting the real physical essence of the process. It's not just active at some environment, like some temperature range, but in large range of environments, then I think we're able to get a more deeper insight. So I just bring some few ideas, but I hope we will have more. So for example, we had this discussion of the structure of clouds, or is it cloudy or misty? And also there's the question of, can you really talk about discrete phases, let's say 2 temperature phases or density phases, or is it really a continuous distribution? Is there a pressure equilibrium between the phases, if there's such, or not, and the role of non-thermal pressure? So all this is also discussed in the context of ISM, all these questions, and the answers are not clear. For me, listening to this and also trying to connect to what's happening in the ISM, I feel it's often the question, I like that Drummond also mentioned this, comparing this cooling time to different other time scales. So it's often the question of comparing the cooling time to different dynamical times. And that what's the dynamical time really depends on where are you at, the CGM, ISM, and also even within these phases. So for example, for the dynamical time, if turbulence is important, could be in the ISM, often this is discussed, it could be the turbulence turnover time, or the coherence time scale of colliding streams. And for the cooling time, then you get a dependence on things like the metallicity and the mean gas pressure or density, which can be also related back to feedback, like supernova or stellar feedback, as papers by Kim and Ostreicher suggest. And just to give an example, I show here a plot from a Siegfried paper. So they made a turbulent box simulation that is multi-phase with cooling and heating. So they shake the box continuously, and they get these multi-phase structures. So these are CNM, cold, neutral, medium, and warm. And this is the density. And what they showed, and others as well, it's just an example, is that if you change the level of turbulence, how strongly you shake the box, then at first, if you barely shake it, you have really these distinct phases of warm gas, WNM and CNM, these 2 peaks here and here, also seen in the density. So in the density contrast is inverse to the temperature, so you have pressure equilibrium. But as you start shaking the box harder and harder, you start losing these 2 phases, and you get a continuous distribution, and you start to populate all the density and temperature in between. And this is actually observed. Of course, this is a very ideal example. Turbulence in practice is not just shaking a box, it's injected by different mechanisms, and that's part of the difficulty, like supernova or gravity. And this is another view of the same idea. So this is low turbulence, where you have this multi-phase of low density and high density, cold and warm gas, and this is at high turbulence levels. And this also connects to the question of pressure equilibrium, because, for example, in the ISM, there's observations of the pressure, of the thermal pressure via UV lines of C1, and the distribution is quite wide, and this is often compared to these simulations that explain this distribution via the act of turbulence. Finally, I just wanted, before I pass to Miao, I wanted to also just say one word. Ben, you mentioned Gaia, and it's actually amazing what Gaia is doing to the ISM. I just have one example I wanted to show you. You still see my screen, yes. So this, yeah. So what you see here is isosurfaces of density of 5 and 25. The numbers here are parsecs, and the center is the sun, and this is not a simulation. This is an actual observation in 3 dimensions. So now with Gaia, so what is happening is people were able in the last few years to produce 3-dimensional maps of the dust around us using Gaia, because now you have the extinction maps of stars from dust and giving you the column density of dust between you and different stars. But now with Gaia, you also know the distances very accurately to many, many millions of stars around us. So combining the column density and the distance, you get the volume density. So people started to produce this this is 1 parsec resolution, 3-dimensional map of the dust around us. So you're actually starting to see the structures in the ISM. So that's a privilege we have compared to the CGM in 3 dimensions. And I think this will also revolutionize the field with Gaia. Okay, so that would be it, I think, from my side. And maybe, hopefully, Miao is now fine with the internet. Miao?
So, can you see my screen? Can you hear me well?
Yes.
Yep.
Okay. I don't know what's happening. Maybe it's a storm right outside the window. But now I connect to Ethernet, so hopefully this time it'll work better. So yeah, thanks Shmuel for the very nice introduction on the analogies and differences between ISM and CGM. I will propose some questions from another angle, which is the ISM's connection to CGM. Like ISM, how does it become CGM? How CGM become ISM back? And what is their their connections basically. So I will propose 3 questions that I find interesting. Of course, if you think of other related questions for ISM-CGM, feel free to post them on Slack. So the first thing I'd like to know your thoughts is about the 2 views of this, ISM-CGM. And we know that, this on the bottom left, this is the down the barrel absorption of the interstellar medium, and where you have a star forming going on in the disk, you have this, you see those strong interstellar absorption lines, and, a lot of gas is flying out at high velocity, and they usually have very large column density. Another view is this, above the barrel. I just made that up, but you know what I mean, this, quasi-absorption line, and then you don't see the disk, but you see through the halo, and you also see, those, absorption lines, and then they have, velocities, offset compared to the galaxy. So my question is, how are those 2 views connected, or maybe not connected? So do we expect, those down the barrel, like those gas that, make those ISM interstellar medium absorption lines, do they become part of the above the barrel CGM absorption, or do they not? So if they are not connected, what happens to those down the barrel ISM absorption, those gas, what happened to them? So that's my first question. Are those two views connected or not? The second question is that, beside those cool outflows that we often observe, don't forget there's this million-degree hot outflows. And usually it's hard to constrain, what is the mass loading, the energy, loading factor associated with those hot outflows. And in recent years, there are many those kiloparsec scale small box simulation that zoom in onto those outflow launching region and see, how outflows are being launched. And repeatedly, what's being seen is that, the hot outflow actually carry most of the energy and the metals compared to the cool outflows. So here I just, put together all those results from small box simulations. And usually the hot outflows contains an order of magnitude more energy than the cool outflows. And also, it's not hard to imagine that they also have very large specific energy, meaning that they can travel much further than the general cool outflows. So the second question is, what do those hot outflows do? Once they are launched outside of the ISM, what do they do to the CGM? And what are the observational evidence related to this question? The third aspect is about elliptical galaxies. So don't forget that, not only star-forming galaxies have an ISM, the elliptical galaxies has ISM too, and it's not as boring as we have thought before. So for example, here, just a very simple experiment, start out with uniform hot ISM, and then just have, type 1a supernova exploding in them. And what we find is that very quickly, the medium become very inhomogeneous. And, while the medium is being overheated by supernova, at the same time, cool gas condensed out of this hot medium. And also the turbulence there is very different from the usual conventional, driven turbulence box that, the results from there. So it's definitely not boring, and there is a lot to learn from it. And the CGM of passive galaxy is not boring either. So this is work from Fari Zahidi, and they find this super solar ion to alpha ratio in the CGM of passive galaxies. So that means that at this late stage of evolution of those passive galaxies, those ion-enriched ISMs still get out of the galaxy and also condense to become those cool absorbers that traced by those ion 2, magnesium 2. So the third question is, how does the ISM connect to the CGM for those passive galaxies? So those are my three questions, but of course there are many more things to discuss related to this ISM-CGM connection. For example, there's this halo interface, there's high velocity clouds. I'm sure we'll hear some from the keynote speaker this week and the next. And then, other questions include how does CGM join ISM or rejoin ISM, and et cetera, et cetera. So anyway, those are my questions, and I hope to see you, share your thoughts and questions on the Slack channel. Thanks.
Okay, thank you, Miao. Thank you, Shmuel.